the lecture. I would like to ask you, because I think I made some, I did not understand well. So as I told you, tomorrow morning, I cannot um, be ready for the lecture at 11 because I have another duty. So didn't we agree to do it in the afternoon or not?
You said you'd check if it is possible we can have it at 4.
Oh, but yeah, I thought it was at 4, but then I I wrote to Patrizia and she told me that you have the exam until 5:30.
Oh, we are not sure about the length of the exam, but it is from 2. We don't know how long it will take.
No, but she told me, okay, but then I think it's better not to fix it. Now, is 5:30 already too late for you or so? Tell me.
Me personally, I have no problem with that. Maybe others will have to say. But it is fine for me.
Okay, can the others speak up, please?
I think it's not a problem if there is like half an hour between the exam and the course because, yeah.
Yeah, but then it's getting,
back.
yeah, then it's too late because I think you have dinner, right?
Yes, dinner is at
7.
7 p.m.
Yeah. So tell me, what about Wednesday afternoon?
No, we have, okay, I don't know.
No.
As if we have tutorial of quantum on Wednesday.
Okay, no.
I think we are free at 2.
Okay. Okay, so let's do the following. Is it okay if we just, because we are supposed to finish on Monday 14. We simply finish on Tuesday 15. Is it okay?
It's fine.
Is okay for all the others? So we just, so this week we have, so tomorrow no lecture. So we have a lecture on Thursday. And then Monday 14 and Tuesday 15. Is it okay?
Yes, no problem.
Sorry, I did not hear.
I said yes for me, no problem.
Okay, so please, I would like to hear from the others.
Yeah, it's okay.
Okay, so I will write Patrizia later this morning, okay? So we just do it, we finish on Tuesday 15, okay? So tomorrow there is no lecture.
Okay.
Okay, so let's start today with I would like to continue to discuss about time-dependent Hamiltonian, and the thing I would like to discuss is something which, so it's, let's say, goes under the name of adiabatic dynamics, okay? Okay, so what I would like to discuss is a situation in which the Hamiltonian governing the dynamics of the system is time dependent. However, it is somewhat slow. So time variations are slow. Slow time variations. Now, what does it really mean slow? Of course, if I tell you slow, it does not mean nothing. Does mean nothing. Okay. So I have to specify And this is something I'm going to specify with more care in the rest of the lecture. You can imagine the following. So each system has some natural time scale. Okay, so for instance, if you take the Hamiltonian, sorry, if you take an harmonic oscillator, then you have the frequency, which is omega 0, which is the natural frequency of the system, and there will be some associated time scale, no, which is the inverse, I mean, of this frequency. Now, you can imagine that slow time variations means that the time scale over which the Hamiltonian, this Hamiltonian will change in time will be, the time scale will be much larger than the typical the natural time scale of the system. Okay, so just imagine the following. I mean, just imagine, so for instance, just to give you a picture, just imagine that you have some pendulum. Okay, so I just make the example in classical physics, but the idea is the same. Okay, and so this pendulum is oscillating. Okay, and it's oscillating with some time scale, with some natural frequency of oscillation. Now, just imagine that you just reduce the length of this pendulum, okay, at a given speed. So you just, like, for instance, you can pull it from one end so that this pendulum gets shorter and shorter, or gets longer and longer. Okay, so you have let's say a typical time scale associated with the velocity at which you reduce or you increase the length of the system, and you have also the natural frequency, the natural time scale associated with the oscillation. So you can consider these two extreme situations. So you can just go very fast, you just change very rapidly the system properties by, so the system Hamiltonian, by, I don't know, just pulling very fast on a time which is faster, on the same scale of the natural oscillation, or you can just do it very slowly with tiny bits. So you just make this pendulum shorter and shorter, but it's very, very slow pace. Now, you can imagine that if you do it very, very slowly, then the system will just, I mean, you can imagine that you will not introduce enormous perturbation, but the system will adjust to the oscillation frequency in a smooth way. So when for instance the pendulum has been shortened by some amount, then the frequency has changed accordingly. But approximately, you will see that the pendulum will oscillate like in its if it was static Hamiltonian. Now, what you saw is that what in time-dependent perturbation theory is that if you introduce a time dependence, then as compared to the static case, so far we studied a slightly different case. We had an Hamiltonian which was H0 plus V of t, okay, some lambda V of t, and so we just use in perturbation theory this phi 0 of n as the reference state over which to construct the perturbation theory. And then we found out that when there is a time dependence, then if you start with initial state I, then you will have transition between I and N. So there is a certain probability that the system ends up in one over the other eigenstates, okay? If you remember, we consider a case in which the perturbation was V of t, which was something like e to the minus t square over tau square, okay? And then we saw that when tau became larger and larger, then the probability of transition were suppressed. So do you remember that we studied the case in which you study from minus infinity in a given state, and then you want to know probability of that the system goes in another state after a long time. And then we saw that when tau was going to infinity, also the probability of transition on states different from the initial, I mean, of course, to state different from initial state, we're going to 0, okay? So what we are going to see is that there is a special kind of behavior when you do dynamics with Hamiltonians, which are very slow. So this is also called adiabatic regime, okay? If times permit, but I'm thinking it will, we will be in time, we will study a very special process of this dynamics when we will consider a special case when we will have a system which after a long time goes back to initial state, and you will see that there are big surprises that will emerge here. Okay, so let me start with adiabatic dynamics. Okay, now you will see that here is difficult. So it's not that we can write down H0 and the perturbation. Okay, so somehow this is a kind of weird perturbation in which the small parameter is the speed at which the Hamiltonian changes in time. Okay, so we have to do something different from what we did so far. But there is something important that you learned in the previous examples. What you learned was that in order to do perturbation theory, it is very important to choose. So essentially, in time-dependent perturbation theory, we have to write down psi of t. So the state is a function of time. Okay, and the state as a function of time will be, so let me call it alpha. So in general, can be expressed as a sum over C alpha of t times chi alpha. Okay, so you just choose a basis, and then you just have the coefficient, and you have to determine the time dependence. Now, of course, you would agree with me that any choice of this chi alpha is in principle allowed, okay? But we saw that when we did time-dependent perturbation theory, it was very important in order for the perturbation theory to work to choose smart basis, okay? Because if you choose a given basis, chi alpha, then perturbation theory is built up nicely. And so far, yes, just a moment, there is a question, I read it. So Jonah asked, can we also consider limiting which the diabatic? Yes, you will see in a moment, okay? So actually there are, so whenever, so the first answer is that you will see that whenever the speed at which the Hamiltonian evolves changed in time, when this is compared to the typical time scale of the system, adiabatic approximation does not work. But I have to specify, so far I still have to specify what is the adiabatic regime, okay? And then you will see automatically when it fails. So the question that I have now is to choose the basis, okay? So this is the first problem I have, because if I choose the basis in an intelligent way, in the sense that captures the main ingredient of slow dynamics, then you will see that the time evolution will be easy to construct in a perturbative way. Now, we saw that in one example, but let's start from this, that when the time dependence of the Hamiltonian is very, very slow, when I stress it, when I say very slow, I'm just I'm comparing some time scale of this h of t with natural time scale of the system, but the slowness will be defined more properly in a second. So when this changes in h of t are slow, then the system essentially likes, if you prepare the system in a given eigenstate, so suppose that you start from h at times t equals 0, okay? At h at time equals 0, suppose that you know a set of eigenstates which I call phi at times t equals 0, n equal en of time equals 0. Now, what I'm going to write will create some confusion, so please ask questions. So at time equals 0, just look at this time, okay? At time equals 0, then the system has a set of eigenfunction and eigenenergies, okay? Now, when I just write this, I'm not meaning any time evolution, nothing. I'm just saying at time t, at time t equals 0, I have a given Hamiltonian, which is this one, and I'm just indicating with t equals 0 the eigenstate and eigenenergy. Just keeping in mind that eigenstate and eigenenergy are well-defined concept only for time-independent problem. Okay, so this is just a parameterization. Now, if you prepare the state in some phi n of t equals 0, now, from what I told you, what do you expect that the system will do if the Hamiltonian at later times changes very slowly? So Do you want to try to answer or should I continue?
Can you repeat the question?
I do not hear anything.
Can you repeat the question?
Yes, but you should try to. Now I repeat the question. So suppose that. So I just repeat it completely. So let's see if. Let's see. So the question is the following. Suppose that I'm consider, sorry, differently. So I consider an Hamiltonian which depends on time, okay? So, and I want to study the time evolution of the state. So I should write down the Schrdinger equation and I have to solve the time dependent Schrdinger equation, okay? Now, so I have to give some initial condition, and the initial condition that I'm giving is that at time t equals 0, the Hamiltonian will be something, I just call it h of 0, okay? And in h of 0, I just prepare the system. So you see, once I have h of 0, it's an operator which does not depend on time, okay? So for this operator, I can define eigenvalue and eigenstates, and I call them, so I just simplify the notation, and I call them phi n of 0 equal e n of 0 phi n of 0, okay? So meaning that I'm just saying, okay, I just take psi at time t equals 0 is given by phi n bar of 0. This is a choice, okay? So I just take the initial Hamiltonian, I diagonalize it, and I assuming that the state is given by this, by one of the eigenstate of this Hamiltonian. Now, the question is, what is psi of t, okay? Now, since I told you that the system, okay, so probably this is too difficult, so I will tell you. So basically, I told you that when the Hamiltonian changes very slowly in time, then transitions are between different states are forbidden. Now, if the system, if transition between eigenstates are forbidden, it means that the system will ideally would like to stay in some eigenstate of the Hamiltonian at that time. So I just repeat the example of the pendulum, okay? If you pull, so if you shorten the length of the pendulum very slowly, then this means that, or you expect that if the system was in the ground state, then upon shortening the length, the system will remain in the ground state of the new, with the new length. Is this clear or not? So this is very important. So if it's not clear, please tell me so I repeat it.
Yes, I think it's clear.
Okay, so can you tell me if, So please speak up if it's not clear. Hello?
Yeah, it's clear.
It's clear. Okay. Now, if this is clear, then what I said before, so the need to choose a good basis to write down the evolution of the state can be that of the instantaneous eigenstate of the Hamiltonian. Okay, I just write here because this is an important thing, and instantaneous eigenstates and eigenvalues. So how do I define this? I define the eigenstates, the instantaneous eigenstates. So look, I even change color, okay? Since I can do it, I just do it in green. That is h of t phi n of t equal e n of t phi n of t. Now, this phi n do not describe the evolution of the system. Okay, these are just instantaneous eigenstate of the Hamiltonian at time t. Okay, so we take this with the hope that by just choosing this as a basis, the evolution of psi will be expressed in a simpler terms. Okay, but just keep in mind that when the Hamiltonian is time dependent, the evolution of the state is just given by this the time dependent Schrdinger equation. And what should be determined is this: psi of t is the wave function in time. The instantaneous eigenstates and eigenvalues are just, as you will see, a convenient basis to describe the dynamics of the system. Okay, so please do not make the mistake then you have a time dependent problem and you assign some physical meaning to phi n of t. Okay, so the state of the system is not, as a function of time, is not phi n of t. What will happen is that in some limit, psi of t is more or less phi n of t. But this is a different story. You have to seek always for psi of t. Okay? So, with this in mind, then we just look for a solution of the Schrdinger equation in these terms. Okay, sum of n Cn of t e to the minus I put h bar to 1, okay, as usual, between 0 and t of dt prime e n of t prime, and then here I have phi n of t. Okay, let's comment on this choice. So if h, okay, is constant in time, if h, so let's consider this example here, okay. If h is constant in time, then obviously, so let me consider this. So let's see how this will become. This will become sum over n Cn of t e to the minus I En times t phi n, right? Because this is constant, I just integrate in time, okay? And phi, I mean, both En and phi n do not depend on time, okay? So this is just symbol that the thing that I expect. Now, I choose to write down the psi t in this form. Sorry, yes. So let me say the following. And moreover, if h is constant in time, sorry, there is something else which is important. Cn does not depend on time, okay? Do you remember this? Please say yes, no, or no.
Yes.
Okay, so I recap. If I consider the case h is constant in time, then going from, let's say, this equation to this relation, then phi n does not depend on time. Cn does not depend on time, so I just integrated, and moreover, Cn does not depend on time. Okay. Now, so suppose the following: if you started with in a given, I mean, I'm saying something very trivial, but I just repeat it. If h is constant in time and you start in a given eigenstate, start in phi 0, okay? Then Cn is just delta n 0. So this means that you will get that psi of t is equal to e to the minus I E0 of t times phi 0. So up to a phase factor, the system will remain in that eigenstate. So I'm saying something very, very trivial, okay? Now, so why I'm choosing this? Well, I'm choosing this because I expect that if I told you, if what I told you is correct, namely that the system, if you prepare, for instance, in the ground state, it will remain in the local ground state, then probably what will happen is that if the evolution of the Hamiltonian is particularly slow, then the Cn of t will be very close to a delta function, okay, if I choose this as a basis. Now, the fact that I choose the exponential in this form is that I have to describe the accumulated phase, and if the energies depend on time, then it's not just energy times time, but I have to do the integral. Okay. So this is a choice that I tried to motivate. If you, I mean, then in the next, I'm going to do a calculation in order to show you that this is actually what happened. And so if you have questions, please ask at this point, because in the next, we are going to apply this idea. So if you have some questions concerning, I mean, if this makes sense or not to you, then tell me now. Hello? Are you there?
Yes.
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 Okay, so please, if I ask you a question, please answer, because otherwise I don't get. So I'm just, so you see, if you don't answer, then it's just I just can record and that's it. But I really would like to understand if this is clear or not. If I don't know, I can speak for 1 hour and a half, which is fine, but then for you, it's a bit a waste of time.
Yes, Professor. Answer.
So is everything clear?
Yes.
Actually, for me, I still is that in the last line you say that the transition rate is 0, so we just have the ground state.
So what is the question?
I mean, I don't get the. I lost the last line. Can you explain it again?
Okay. So so far we did the perturbation theory by just writing down H0 plus lambda V, okay? So perturbation was just considering V very small as compared to H0. So
Yes.
the reference, the starting point was the set of eigenstates of H0, okay?
Yes.
Now, today, we would like to solve a different problem in which H itself is not written as H0 plus V, but it's just what is small is the fact that the speed at which H is changing in time, okay?
Yes.
So what should be the reference point? The reference, so if there is no change at all in time, then we know how to solve the problem. It's just the time independent Schrdinger equation. We have a set of eigenstate and eigenvalues. Okay. So if the change in the Hamiltonian is extremely slow, just unimaginably slow, then you may expect that the system will look almost like a time independent problem. Okay? But if it looks like an almost time independent problem, this means that I should use the some eigenstate and eigenvalue of h of t. Because if h of t does not depend at all on time, then what I wrote in green is the solution. But if it depends in a very tiny way, in tiny manner on time, then the system, well, it's almost time independent. So if I ask you, okay, should I take the eigenstate at initial time, or should I take the eigenstate at final time, or the eigenstate at middle of time, to just decide to use this as a reference point? So in principle, you can take whatever you want, okay? However, it turns out that a more elegant, a more meaningful choice of basis is not that one to say arbitrary, I just take the initial time, the final time, 2/3 of the final time, whatever, I just take the instantaneous eigenstate and eigenvalue, and I suppose to write down the wave function as sum over n Cn of t e to the minus this integral of en phi n. Why this is a good choice? Well, in order to understand if this is a good choice or not, let's consider first the limit in which h is constant in time, okay? So there is no time dependent whatsoever. Let's see how this expression square reduces in this particular case. In this particular case, then phi n of t becomes phi n because it does not depend on time. The exponential, the integral can be done directly, easily, and I get just the standard phase, and Cn of t becomes time independent. In particular, I just noticed that if I start in a given eigenstate of h, then obviously the system, since Hamiltonian is time independent, it will remain in that eigenstate, which means that Cn will be just a delta function, and the evolution at later times of the wave function will be just phi 0 times a phase factor. Okay.
Oh, I get it. Thank you.
Okay, good. So why this is a good starting point? Because we know that when we do changes which are very, very, very slow, super slow, super slow, then transitions between different eigenstates are suppressed. This is something we discussed previously. So it will look like that this starting point will be a way to just single out then the changes in the dynamics due to the fact that the states, the eigenstate change, and also the transition between the eigenstates. Okay, so I mean, this is the idea. But so far you may say, look, all this may be completely wrong. Okay, we don't trust you, which is fine. Okay, I simply try to motivate this, but then I just rewrite this here. Okay, so I'm just taking psi of t and just.
Sorry, Professor.
Yes, just a second. Just rewrite this formula and then you. Okay, otherwise I get. Just a second. Huh? Yes, tell me.
I wanted you to repeat your when the Cn becomes a delta function.
So if I start in a given eigenstate phi 0, okay. So I remind you that h, when h is constant in time, Cn is just given by psi of 0 phi n. Okay, this is Cn. Sorry, this is the star. Okay. Now, if you start in phi 0, this means that Cn is just a delta function. So if you prepare the states in a given eigenstate and the Hamiltonian is time independent, it will remain there forever. Okay?
It's okay.
Okay. Now, look, something which I really would like to stress, and it is very important. So please do not give a dynamical meaning to phi n of t and en of t. These are, for the moment, they are just a solution of this eigenvalue equation, okay? What you know, which is the correct thing, is that when the Hamiltonian is time independent, you solve Schrodinger equation, time independent Schrodinger equation. And when it's time dependent, you have to solve this one, okay? So this is just something which is very useful, and you will see why. Now, something important, let's assume that the eigenspectrum is always degenerate, okay? So En of t is different from Em of t if n is different from m for any time, okay? This is an important simplification, which, I mean, embraces the number of important states. If they are degeneracies, the thing becomes much, much more complicated. So our goal is to study the Schrodinger equation. So I have to take this Hamiltonian, this psi of t, and I just substitute in the Schrodinger equation in order to get an eigenvalue, a set of equation for the C, right? So what I have to do, I don't do all the steps, but just give you the idea. What I have to do is just to take the derivative of psi of t, which is just equal to sum over n over c dot n of t times e to the minus dt prime en of t prime times phi n of t plus sum over n cn, then I have minus I e n of t e to the minus I integral over dt prime en of, here this prime, okay, of t prime phi n of t plus the state depends on time. So you have to take the derivative of the state, okay? So I just write it, e to the minus I integral over of dt prime e n of t prime. And then I have, I just write it like this, okay? Don't be confused, but this is, so I put phi dot, okay? So phi dot of t is nothing else than d dt of phi of t, phi n of t, okay? So I just take this and I write down the second term, and then I multiply both sides with phi m of t, okay? So I have on one side, so I have here the Schrodinger equation, okay, psi of t equal h psi of t. I just write down all these things. I multiply by 5m, and then I find a set of equation for Cn. So in the set of equation, you will do it yourself, so you can verify. C dot m of t is equal to minus phi m of t, phi dot m of t times Cm of t minus sum over n different from m Cn, then we have phi m of t h dot phi n of t E n minus E m e to the minus I integral dt prime E n minus E m. Okay? Okay? So you have to do all the steps. Hmm? Is this okay? I do not hear you.
Yes.
Sorry?
I said yes. Yes, we will verify it.
Okay. So you have to verify. So I told you all the steps, and you will find something of this kind. Now, let's analyze first this term here, the second term. Okay. So can you tell me, is there a regime in which the second term becomes 0? Or tends to become smaller and smaller? Any suggestion?
The energy difference between N and M are big.
This is a good option, but so is there an other way to see this this limit?
Expectation value goes to 0.
Yeah, essentially, so you both pointed out, so essentially what we need is that this term here is much smaller than 1, right? Okay. Now, I just pointed out something which is very interesting. That is h dot here. So this means that if, hello?
Yes, I think the Hamiltonian should vary very slowly.
Yeah, right. So what we want is that when the Hamiltonian, sorry, let's put it this way. When the Hamiltonian is time independent, this term becomes exactly equal to 0. Okay? Which is what we found, what we knew already. But what is very important is that when these matrix elements, so actually, I mean, when these matrix elements are much smaller than 1, which means, sorry, not the matrix element are much smaller than the corresponding energy difference, then this ratio here is much smaller than 1. So what does it mean? So suppose that, suppose the following. Suppose that the Hamiltonian is something simple, okay? Let's take of this form. Okay. So what is what is h dot in this case? H dot is hf over T minus H initial over capital T, right? Okay.
Yes.
Yes.
Very good. So in this case, so this is just to give you an example. In this case, if I take this term here, this is equal to some matrix element phi m of T, then I have HF minus HI phi n of T, okay, which is something, and then I have T times En minus Em, okay. Now you see that this will be something, okay. Let's not spend much time on this. We can be more refined, but say that the important idea is that in order to have all these terms much smaller than 1, is that I want to have the time over En minus Em much larger than 1. So in this case, the time, I mean, since we have a linear change, the time scale is just capital T. So we want that the time scale of variation of the Hamiltonian should be much larger than the inverse gap, because we can define some time scale tau n m, which is h bar over En minus Em, okay, of T. And this tau defines all the various time scale of the problem. If this was an harmonic oscillator, then all the energy difference will be multiple of the frequency omega 0, and then as a result, then we should take the minimum of this frequency, which is omega h bar of omega 0. So if the time scale of the variation of the Hamiltonian is much larger than all the time scale of the problem, which means h bar over the various gaps, the various energy differences. If this happens, then we can drop out the second term. But if we can drop out the second term, then you see something interesting. You see that then each Cm depends only on Cm. This means, in particular, that if you start, is this clear so far? Hello?
I missed a point where you said where you have to neglect the second term, the last bit of it you were saying.
So I just took this example, okay, in which h of t is just this linear change between hi and hf. So if I take the time derivative, this is proportional to 1 over capital T, okay?
Okay.
Now, this means that when capital T times the all possible energy difference is much smaller, much larger than 1, this term will be much smaller than 1, okay?
Yes.
So indeed, on increasing the time, then this term becomes smaller and smaller, okay? So for very large times, so I can drop out this term, and then I just remain with the first line, with the first term. C dot m is equal to Cm, or to something times Cm, okay?
Yes, thank you.
Now, what does it mean, this? It means the following. Is it okay? I just erase this so that we just are on the same page, okay? So if C dot M is equal, let's say, to minus phi M of T phi dot M of T, Cm means that, what is the solution to this equation? The solution is just Cm
Exponential.
of T
Right.
exactly is equal to the e to the minus integral of dt prime of phi M of T phi dot M of T T prime times phi Cm of 0, right?
Yes.
Yes.
Very good. Now, I will discuss this exponential in a second, okay? Because there are, so I'll change page, so that I just rewrote here. We have said C dot M is equal to minus phi M of T phi dot M of T Cm, okay? And then we saw that Cm of T is equal to e to the minus the integral Cm of 0, okay? So now let's suppose the following, that I take at time equals 0, psi of the initial time is nothing else than phi 0 of 0. Okay, so I just start in a given eigenstate at the initial time, right? So this means that in the expansion I wrote before, that is psi of t is equal to sum over mcm of t, the exponential phi m of t, Cm at time 0 is just nothing else than delta m0, right?
Yes.
Okay. I want to hear the others.
Yes.
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 Yes,
Okay.
yes.
So, but then you see that this means that C, in this limit, Cm of t is just equal to the exponential times delta m of 0. So the time dependence is just an exponential times delta m of 0. So if you started in a given initial eigenstate, the system will not change eigenstate, because if I substitute this solution in psi of t, then what I found is that psi of t is equal to e to the minus the integral of dt prime phi n of t prime phi dot this n of t prime times e to the minus I integral of dt prime of e 0 of t prime times phi 0 of t. So what we see is that in the limit of very slow changes in the Hamiltonian, the dominant solution, so this is called the adiabatic solution, tells you that the dynamical state will remain in the instantaneous eigenstate up to certain phase that I will discuss in a moment. So you see that the choice that we made in representing the state using the instantaneous eigenstates and eigenvalues, it turns out to be very useful because in the limit of very slow changes, this confirms actually the intuition that we had that the system will remain in the instantaneous eigenstate. So just to transfer this in some picture, so if you take the Hamiltonian of an harmonic oscillator, you prepare it in the eigenstate, okay? And then you change. So let's do it. So you take the Hamiltonian of omega 0 times a dagger a, okay? Or let's do differently. So I just tried it. Okay, so it's p squared over 2 m plus 1/2 m omega square x squared. Okay, so you just have it. You prepare the harmonic oscillator in a given, so a particle in a given trap. So then what you do is just to introduce some frequency. Okay. So for instance, this means that you just close the trap. Okay. So you go from one frequency omega 0 to some, or initial, to some frequency omega final. Can be much of this type, but then you do very slowly. Okay, so you do this change in a very large time as compared to, I don't know, to typical frequency of the harmonic oscillator, and then you will see that if the system was originally prepared, say in the ground state of the black curve, then so I'm not able to draw it, then after some time it will remain in the eigenstate of the red potential. So there will be no excitations created in the system. This is the essence of what is written here. The evolution of the system is governed by an Hamiltonian that makes the system evolve in a state which is the instantaneous eigenstate. Questions? So I cannot believe that everything is clear. This is beyond my imagination. So is everything clear?
I'm sorry, it takes a lot of time to digest everything. So
very good. So since you are not digesting, then you should tell me what did you not digest. I'm happy that it takes time to digest.
Well, I'm still reviewing the steps, but I understand a bit, but not all. With regards, I think to but I think I need to solve it first because I would
okay.
like.
Okay, so then let me say the following.
Okay.
Is the physical picture clear? Let me say the following. I mean, you have to redo the step, then I understand. But is the physical picture clear?
Yeah.
This is the most important thing. Now, there is something which is written in front of you, which should perturb you a lot. So I wrote this, okay? Then of course there are corrections which are small or large. And I would like to come back to Jonah's question. So Jonah's question now is a good time to some notable examples maybe okay, of non-adiabaticity. Well, now you should see that the difference is that when this term cannot be disregarded, that means that the evolution of Cm of any Cm is coupled to all the other n. This means that even if you start with the ground state and you do a perturbation, a fast perturbation, then you will populate also states which are different from the ground state. Okay, so you create excitations in the system. So I don't have. So
Yeah, somehow I understand. Like in the
so
when the case.
Yeah, go ahead. Go ahead.
I mean, is that you mean that in the case we have the excitation, it mean that the adiabatic is fails.
Yes. So just imagine the following. So do you see the pendulum? This, do you see it in the?
Yes.
Okay. So just imagine with some imagination that this is a linear pendulum and it's oscillating in some state. Now imagine that I just reduce the length. So you see that probably it will remain oscillating like a good pendulum, but with a different frequency. Of course, it's difficult to see it. Now just imagine the following.
Yeah, it's clear.
It's oscillating and you do like this. Okay, do you see that now it's doing crazy things? Okay, this is the difference between adiabatic evolution and non-adiabatic.
Yeah, thank you. It's clear.
Okay, the adiabaticity is a concept which is valid also, which is important also in classical. What I'm saying is that in quantum mechanics, the adiabatic translates in the fact that
I'm sorry for interruption, but suddenly I think that I lost connection some second ago. So
okay.
you talk about quantum mechanics and then I lost.
I repeat it. So what I want to say that adiabaticity is a concept that applies also in classical dynamics. Okay, the example I gave you is classical. When we look at it in quantum mechanics, it translates in the fact that if you prepare the system in an instantaneous eigenstate, it will remain in the instantaneous eigenstate with no transitions. This is what I want to say. Now we have 15 minutes. I want to spend some time to give you some couple of exercises. However, before that, I really would like to discuss now. Do you think, I mean, are you worried about this expression or there is something fishy? I mean, the expression is correct, so don't worry. But is there something strange there or do you think everything is okay? Now, let me say, so first of all, the state is always normalized, right?
Yes.
Yes.
Okay. So now, since this is I mean, so first there is this term here, which is e to the I. So when you do the sandwich with the complex conjugate, then everything is okay, right? Because it's just a phase factor, so it's cancelled. But now, aren't you worried by this exponential? So is it correct or is there something strange?
I mean, it comes after you input the expression of delta m comma 0.
Yeah, but so in order to be correct.
I think it's like of I.
Right. So in order to be this correct, so that the normalization is kept correct, this means that phi times phi dot should be imaginary. Because if this is real, or if it has a real part, this means that there is a decay, so that normalization cannot be preserved. Okay. Now, what you have to try to do is just to prove that this is imaginary. Okay. Now, I suggest you to do the following. So this is an exercise for you. Just prove that phi dot is imaginary. And so you can prove it. So just take the derivative of dt of phi. Okay. So just take n m m. Okay. Now, this is clearly 0, okay? Because this is 1 and the derivative of constant is 0. Now, if you use this, then you can easily show that phi dot is imaginary, so everything is fine. Now, there is something very interesting associated with this phase. This is something which goes under the name of Berry phase. We do not have time to discuss it now. Now, we have 3 lectures to go. And we have to do second quantization. And I really would like to spend some time doing also this, which goes under the name of Berry phase. Okay. This is something weird which happens in the dynamics of quantum mechanics, that it was, people never realized that this phase could be measured. And let's say on Thursday, I will tell you a little bit more about this. Now, before we go for lunch, then I want to assign 2 exercises, okay, which are very simple, no, not very simple, but you have to do it. So suppose the following. Suppose that you have an infinite square well, okay? And you have a particle in the ground state. So psi of t, so psi of 0 is just the ground state phi 0 of L. I just call it L just so that you see what I mean. Okay. Then at time t plus, so at time t 0 plus, okay. At time 0 plus, I just double the, okay, I just open and I double, okay. So the question is, I want to study the states as a function of time, okay. In particular, I would like to know the probability as a function of time. So this becomes, so this L, this is 2L. And I would like to know the probability, a function of time, that the system is here, remains here, okay? I just call it t lesser than L. What is this? This is nothing else than the integral of dx of psi x modulo square and t, okay, between, so let's say 0 and L. Okay. Is this clear?
Yes.
Okay. May I go to a second exercise that I would like to assign?
Yes.
So the second exercise is similar, but so you have a square well again. Okay, so this is 0, just take it minus L over 2 and L over 2. Okay. Sorry. So you have to study the following problem. So it's not a square well, but it's a square well with some bump in the middle. Okay. And this bump has height V0 and length L. Okay. So you should assume that this has, can be treated in perturbation theory. Okay.
Yes.
Okay. So try to do, so this is time independent perturbation theory. This is time dependent. Now for time dependent, I remind you, actually, I really would like to add something. For time dependent, it is important that if you want to study psi of t, then that it is important that you express the initial wave function in terms of eigenstates of the 2L well, because then the evolution will be much simpler. Okay. Now, sorry, I really would like to add a second part to this exercise. The second exercise.
Sorry,
Yeah.
Professor. What's the question in the second case?
Here, this
Yes.
one.
Yes.
So you have to find the eigenstate and eigenvalue in perturbation theory. Okay. So let's do the following. You just find the correction, the first order correction to the eigenstates, and first and second order correction to the eigenvalues, if you manage. Okay. Okay, good. For this part, I forgot to say something. So in the first part, I told you you have to do it fast. So at time 0 plus, you just open instantaneously from L to 2L. Then you do the following, that you just introduce L of t as t over capital T L plus 1 minus t over capital T to L. Okay, introduce this time dependent length and study the dynamics in the adiabatic regime. So what I told you before. Okay. So tomorrow we will continue. No, not tomorrow. Thursday we will continue on the adiabatic regime. Then we will do second quantization, and that's it. So just to recap, because I'm going to send a message to Patrizia. So tomorrow, no lecture. And then we will have Thursday at 11, Monday at 11, and the last lecture on Tuesday at 11. Is it okay?
Yes.
Yes.
Okay.
Yes.
Perfect. That's it. Do you have questions or I mean, there is no point. I mean, we have 5 minutes, but I have no time to start a new topic. Okay. So have a nice lunch and see you next Thursday. Okay. Bye-bye.
Bye.
Bye-bye.
Bye.
Bye.
Professor? Professor? Oh, okay. He's gone.
Oops.
What is it?
Professor Valerius is speaking.
You guys going?